Rolling.
Hey, welcome, Internet. We are doing a lunch and learn today with a special guest. And without further ado, I present to you my friend, Eric Redmond. He is the author of 7 databases in 7 weeks. So, there you go.
Woohoo.
How you doing? Today I'm going to be talking about 7 databases in 7 weeks of the book, but I'm going to try to cut this short, so that's why I put 7 databases, 17 minutes. This does not mean that you're off the hook from actually buying the book. It's just that this will give you a preview of what to expect when you actually go about reading it. You might know me better as Kodoroshi on Twitter, because apparently, I don't know, that's a better name. So I'm thinking about just changing my name to that, since people will be like, it's like, I'm Eric Redmond. Oh, Kodoroshi. It's like, yeah, okay, that's me. As everyone runs into. So anyway, this is the title of the book. This is what the cover looks like. Me and Jim Wilson wrote this book. And generally, the idea of the book wasn't just to talk about the databases themselves, although the implementations are really important, but we were sort of following the model that Bruce Tate put forth in 7 languages in 7 weeks. It came out a couple years ago. It's important to learn. His philosophy was it was important to learn the individual languages, but equally as important as those were largely a gateway of learning different ways of doing different tasks and learning the strengths that different languages have over others, and sort of followed the same model. Now, unfortunately, there's really generally only about 5 different broad categories of databases. So in a couple cases, these are redundant. Luckily, there's enough differences between the 2 redundants that it's still interesting enough. But Relational Database, everybody's familiar with this. I don't even need to go over that. Graph Datastore is probably the newest out of this variety, and it's the idea that rather than having a schema or anything structured like that, you just throw data out in nodes, and it's the relationships between those nodes that you can just add willy-nilly. And the way you create is you just sort of walk through, you start at one node, then you walk out, which is fantastic for an entire class of problems, like, for example, thread or any sort of social network is the obvious case, but even less obvious problems like rack systems, like where you're sort of like role access control, things like that, because they generally tend to be a little more graph-based than you would think. Common data stores, I'm not going to go over too much. Those are sort of like big table, like the Google big table. You've probably heard of Cassandra, or HBase is the one that we cover in the book. Those are really for like ultra huge scale. I mean, the companies that actually need something like this, like you can count on your hands. But they're really interesting. That said, although the companies actually need a columnar data store to be able to massively scalable, you can count on your hands. That hasn't stopped, thousands and thousands and thousands of other hopeful companies from adopting this technology for absolutely no good reason whatsoever, because they want to be huge. Key value stores, there's sort of 2 different styles that we talk about. Riak, which is sort of the Dynamo style key value store, which is what Amazon uses as their database, and not Riak, but Dynamo, and Redis, which is sort of the key value store most people are more familiar with, which would be something like Memcached, where it's just kind of generally often used as a caching layer, but there's a lot more coolness to this than Memcache has. And then finally, document data store. This is what people generally think of when they think of NoSQL. Think of Mongo, CouchDB. These are all document data stores, which effectively, rather than having any sort of schema, you just stick in what are called documents into your collections, and those documents are just JSON document objects. There's nothing requiring them to be JSON. They could easily just be XML, but JSON is apparently just the one that people prefer to use. So this is sort of the graphic that I enjoy. It's an overview of the database ecosystem of all the different styles of databases and what they're often used for. You've got the relational model, on this side and the non-relational on this side. Well, we cover these in the book, so which is, you know, a drop in the bucket of the overall ecosystem. But again, the point of the book is to run you through these specific implementations, so you sort of gain an understanding. Hopefully, you can extrapolate what you learn to understand pretty much this entire ecosystem. So, relational models, I'm not going to talk about this much at all. I mean, I would like to go over a 1,000-foot view of this. Postgres, relational database, 40 years of work on the topic. You should definitely give it another check, because even if you think you know everything about Postgres and everything about relational database, still check out the book, because I go over some really weird things that people probably aren't used to. This is one of my favorite queries. This is actually it's a shorter version of the book. I only have 3 dimensions here, but the book actually has 18 dimensions. So it's doing a bounding cube around a point in 18-dimensional space and saying find all the nearest neighbor matches. I dumped in a bunch of movie data into this, and then thought, oh, you know, find me, using a similar query like this, find me the point that's closest to Star Wars, and then rank them. And of course, you know, Star Wars 5 and 6 popped up. But then a movie I'd never heard of called Krull, which apparently is like a sci-fi movie from the 80s, 83. Krull popped up, and I'm like, hey, hooray, it works, because I just learned something that I absolutely didn't know at all. But the reason I say to the ORM obsessed is don't be afraid of SQL. I mean, don't try to shoehorn AREL or anything like that, because honestly, it wouldn't make a query like this any clearer, and it certainly wouldn't make it any more portable, because this crap only works on Postgres anyway. So that's sort of the end of that little rant. There's other relational databases, and they have different utilities. You know, MySQL, Drizzle, Volt. Somebody asked about recently. Yeah, is pretty awesome if you're doing sort of like large scale kind of thing. So I definitely check that out if you really love the relational model, but you need it to sort of shard or scale across multiple instances and use that. Big table, columnar. These are the you know, this was the data store that Google invented, not HBase, but big table. And I'm going to have these slides available if you guys want them, but these are sort of the gems that I would recommend if you need to interact with it. But again, almost nobody does. But this is sort of an idea of what a columnar data store is. Rather than a relational model where data is stored in rows, instead in these tables data is stored in columns. Now this might seem like not a big deal, but it actually affords you a ton of benefits, one of which is sort of built-in versioning. So, and you can version, you know, individual column values. So imagine doing something like a wiki where the title might be fixed, but you're going to have multiple versions as edits go, and you just want to save every single one of those edits and say, okay, well, just give me the most recent version, and that would sort of implicitly be a row, but there's nothing, it's not actually stored as a row. The other thing is you can store, you know, it's great for like doing weird like data center things, where you can say, okay, well, you know, these different families might live in different data centers. Because these two might live together because they're accessed quite often, whereas that third one might be, you know, some sort of like caching data that you'll data warehouse and look at eventually, but they don't need to actually live with the data for performance reasons, and it's never generally queried. This is sort of what it looks like using column data stores. The problem with column data stores is they don't really have any sense of like indexing or anything like that. They just have these keys, and then they have these column families. So if you want to index, you often have to just make up your own index, and then you effectively create your own other row based off of the keys that you want to query by, and then point it to the other. So you're effectively writing your own index on your own. But it's a lot of scanning. This is sort of what it looks like. Where we would be, for example, getting, you know, the top 10 versions of out of a wiki. And there's no sort of ORM or anything like that, but there is thrift. which is originally a Java project, but there is a Ruby implementation. You generate these Ruby drivers, and Thrift is sort of a it's sort of a protocol for interacting with column-oriented data stores. The nice thing about Thrift is it actually does live up to the promise to some extent of the fact that you can swap out different implementations. Again, something you almost will never really do, but you could. But more to the point is you just only have to think about it in one way. And you can use HBase or Cassandra or Hypertable or any of those that support it. Yeah, and here's some other columnar data stores we're taking a look at. I should mention also Hypertable does have this thing called HQL. Google also has, if you've ever used, what's it called, the Google App Engine, they have their own query language called GQL, sort of similar to that. It looks kind of SQL-ish, but it's not. You can't do joins or anything like that. Document Data Store, Mongo, Couch, these are the big things. One thing I will say about document data stores, if you're doing sort of highly related data and you're mapping it this way, don't try to denormalize, because it's probably the worst thing you can do. Because these columns don't join on the back end. These collections don't join in the back end. So if you've got a collection of users and you say, okay, well, I want to have a permissions table over a collection over here and a users collection over here, and then the users will point to that permissions table. No, absolutely not. Because effectively what you're doing is, even if you try to join it, you're really pulling the data on the client, and then you're pulling the permissions to the client, and then you're joining them manually. Even if you think you're doing it on the back end, it's still doing it manually. In that case, what you should be doing is nesting, and that's the whole point of the document data store, where you'd have the user and its permissions would then be nested inside as an array of values or a hash of values. This is what a document looks like. This looks like JSON. This is actually a Couch document. The _rev, sort of one of the big differences between Couch and Mongo is that Mongo does updates in place. So you sort of have actually I'll show this, you have this sort of big Mongo cluster, and you interact through, if you get sharded, you interact through this service called Mongoose, and it manages everything and makes sure that these replicated values are kept up the same. For example, these manage themselves, make sure the replicated values are kept up the same. This manages the shards and makes sure that your keys are sharded correctly and all this. But at the end of the day, you're still updating documents in place, as opposed to something like Couch, where it has these revisions, and you're just connecting to one out of someplace. So there's like a big Couch implementation. You would just randomly be connected to one, and the value on this very well might not be exactly the same as the value here. So the way it deals with that is it says revision numbers. So then, if you would try to update this with a revision that's wrong, then it will return error and be like, hey, you need to provide me the most recent revision key so that I know that you're updating the most recent value. So that way it stops conflicts from happening. And you can set these to be automated and just be like, I don't care, I just take whatever value I give you. But generally you're going to have to deal with that in your code. This is what the interface for Couch looks like. It's much prettier than the interface for Mongo. There's just a HTML screen you can get servers on. It's not really meant to be interacted with. That said, Couch is very REST heavy. If you love doing RESTful interactions, then Couch is definitely your thing. Mongo has sort of wrappers that wrap around it, but that's not at all what it's really for. It's kind of a cheap shot, kind of comparing these, because they are going after two different audiences. But my short answer is, come on, Mongo, make a better interface. It's like you're a giant company and you're the number one NoSQL database. I think you can handle this. They just need a higher designer. One of the things about these sort of NoSQL databases, and I just mentioned this because Couch, especially Mongo, supports MapReduce, but don't ever use it. Couch, on the other hand, that's how you query it. You don't get this cool little query language like you do with Mongo. You have to write MapReducers, and this is just sort of what a MapReduce would look like in Ruby, just straight up Ruby code. The idea being that you sort of take a collection of values and then you map it in some way. This is sort of a standard Rails syntax, which of course really internally is doing this. Or it's just saying, in this case, you extract all the capacities out of the room into its own array. So now it's just, you've mapped it, you've converted the array from one type of data to an array of a different type of data. And then you reduce it, in which case you are now just sort of summing together all of those values every time. For every single element you say, add this onto the previous total, add this onto the previous total, and then you get your result. So this would just be adding up the total capacities of all the rooms in a hotel. Now you might wonder why. Why would anybody ever want to do this? Well, this is actually really useful when you've got sharded data, when you've got data that's sort of distributed across multiple machines, because you can just say, okay, this machine right here, you're going to map the first half. All the values you have, you map those. Second machine, you map all the values you have, and then you reduce them into some result, and then you can re-reduce those results into even more results, and then you end up getting your value. This is important because it's much less expensive to give the algorithm to where the data is than to pull the data to you and then execute your algorithm. It's very, very expensive. I mean, imagine you got terabytes of data and you wanted to sum all the values, and you just had your client being like, oh, give me the next value, 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 as opposed to just send it to the servers and say, hey, you guys execute this, give me a result. Mongo versus Couch. I would say these are probably big points that are different. But generally, what I say is, if you need super high durability and you need to like embed, for example, services, Couch, you could, there's an implementation right now called Pouch. It's like a JavaScript implementation that you can run on a web client, but it's entirely at parity with Couch. So the idea being that you could even have a whole bunch of web clients doing all of their sort of client-side things, and then you've got a cluster of couches out there that you would then sync with. Mongo has no concept of this whatsoever. Mongo is very much a centralized service, where and that's what I always say, it's web scale. It's like it's really for that kind of problem scope. But if I were, for example, writing like a medical software in Haiti or something like this, and I had really poor access to the internet, and I needed to be able to store values in a database and then have it sync up with a master at some later point in time, I would use Couch. I would never use Mongo for something like that. So, the other thing is that, but that said, Mongo is actually much easier to use. So if you're coming from the relational, I guess I should back up, because Couch guys give me a hard time. I think it's much easier to use because I think it's much easier to say, hey, collection, give me a count of these values, or do more of a SQL-like query and say, find me all the values that match this, or match these criteria, and index them. I think that's much easier than writing a MapReducer, which is what you have to do with Couch. Couch only interacts, there's no query language for Couch. You write a MapReducer for everything you want to do. And finally, penultimately, key value stores. I mentioned that there were sort of the two different varieties. We were React key value store and Redis, which is a key value store, but it's more of a caching key value store. React is it's pretty documenty in the fact that your value can be literally anything. I mean, you could stick your value can be an image. It's you interact with it using REST. And then if you said, okay, well, the key for slash, you give it bucket, so bucket slash images slash, I don't know. I'm trying to think of something that's not awful, that every image that people know. The only one I can think of that everybody knows is like Goatsy or something. All right, so yeah, .jpeg. You put it out there, and then when you do a request, it will return that value. It will return that image in the form that you stored it in. And you can do that with
no encoding issues or anything.
Because it stores everything in basic form. Okay. So it's very web. I mean, it speaks web probably more and better than any other database out there, because everything's encoded in base 64, and so as part of the storage, header, you would just give it a content type and say, okay, your content type is concept was for ultra high availability. If you can't be down for a fraction of a second, or more importantly, if being down for any amount of time or lagging for any amount of time is costing you money, you definitely want to look at React, because that's really where its strong suit is. And the reason it is because it has these consistently hashed clusters. This might look similar to Bigtable because Bigtable is very much also jumps on this same concept, where you've got this called consistent hashing ring. The idea being that data is automatically replicated to a certain number of nodes, and you can request from any of the nodes, and if it doesn't have it itself, it'll try and pull it, or it'll redirect you, internally to where the data actually is. And you can do all sorts of cool things that you can't do with other databases. Probably the biggest one is called NRW, which is the nodes writes nodes reads and writes, and what these values are is you're defining how many physical nodes you want to replicate a value to, how many nodes have to be written before the write's considered successful, and how many nodes you want to read from before it's considered successful. And this is very powerful when you're talking about a distributed database system. Sort of the sort of default is called a quorum. So if you have 3 nodes and you write to only 2 of them and you read from 2 of them, you're guaranteed that you're going to get the most recent value. So in this example, say that version A already exists on all these nodes, and then you write version B only to these 2 nodes, and then you read from 2 other nodes, that overlap is going to happen. A quorum is the number of nodes you have divided by 2 plus 1. So in this case, 3, quorum is 2. Write quorum, read quorum. But you're going to get both values back, and then you know that, this one was written afterwards, so it's the most recent version. You can do all sorts of weird things like this too, and this is why I talk about ultra high availability. You can write to just one. I mean, if you read, because obviously the more you write to, the slower the write is, because it's got to return and say, okay, I've written to all my nodes. So if you set W to 3, you will be consistent, because the write will write to every, so if you've got thousands of nodes, say, okay, every time somebody writes to the database, write to all 1,000 nodes. It'll be really slow, but you know that every successive read that happens is going to get the most recent value. On the other hand, if you're really interested in having fast writes, you can just write to one node. And if you don't care how, like logging, for example, you just log, just write to one node, I don't care. And then when you read, you just read from all the nodes. You've slowed down your reads considerably, but your writes are super fast because you're only hitting one node, but you've read from all of them. So again, you're guaranteed the most recent value. If you don't care about consistency at all, just set write to one and read to one, and then you'll get a value. But it'll probably be, especially the more nodes you have, it's like you're really going to be out of sync. If you have 1,000 nodes, you only wrote to one, and then you're reading from some random one, you're going to get a value, but it's not going to be probably the right one. So this tunability is probably at the heart of why React is so powerful. And when I talk about high availability, it's because this node could go down, but since I'm reading from, I just say, read from 2 nodes, I can still read and I'll still get a value. Same thing with write. This node could go down and it'll write to the other 2, and I'm still up and running. I think Justin Shee, the one of the project leads, said that we created React so that we could go back to sleep at night, because the idea being it's like their servers would crash. Servers always crash, and crashes, they can just be like, okay, well, we'll deal with it in the morning, hang up the phone, and they wake up the next day, and then they spin up that server. It's not really a big deal. It's very highly available. Redis, amazing. I can't see enough good things about Redis. If everybody here hasn't used Redis yet, I highly recommend downloading some Redis projects and play with it. There's a really good site, the Redis Cookbook. They show all sorts of cool, funky things you can do with Redis. Unlike a standard key value store like Memcache, where it'll just have a key of a string, and then a value will be a string, Redis can do things like lists. You can push lists of values and then say, oh, give me back all of the contents of the list, or just give me a couple. It can do hashes as well. In this case, you've got your key, which is conferences, and then the hash field, and then the hash value. And finally, you do sets. And this is the one that I actually think ends up in reality becoming the most useful, where you can just push values based off a key. So this set now of person contains 2 names. I can then create a different set called owns pet, and then do the intersection of these 2 hashes of person and owns pet, and then it gets me. I mean, that's pretty amazing to be able to do with a key value store, to be able to do intersections and unions and differences, so you subtract set values. As if all of that wasn't cool enough for a key value store, we can also do cool stuff like pub sub. Like you can do publish, subscribe, so you've got your one client just acting as your publishing server, and then any number of clients subscribing to that server. And Rescue, if you guys have probably used Rescue before, internally uses PubSub fairly heavily. It also uses, I believe it uses blocking queues as well, which is probably, to me, the most interesting use of these lists. So rather than just saying, L range, you can pop values out of a list as well, just like you could with any other list. But you can actually do a blocking pop and say, okay, well, I'm just gonna wait until I get a value, and then when some other process finally pushes a value onto that list, then whatever client is doing that blocking pop, now it gets that message. So it's a really easy way of sort of doing these buffers. And there's other key value stores too, but I have no opinion on it. Finally, Graph Data Store, which is pretty awesome, Neo4j. I already mentioned this earlier, where you get your nodes and then your lines in between those, and this made me laugh. This is a graph database modeling kit. That's pretty much all you need. If you're going to be interacting with Neo4j, you use the REST interface, because it is a Java project. So unless you feel like running on JRuby, you're not going to be interacting, sort of directly in the engine. That's actually, I think it's good that this REST interface has really been getting a lot of mind share in the Neo4j community, and they're very much moving this direction. So much so there's this big project now called Cypher that you guys have been using for Thread, and this is what it looks like. So you, again, as I said, you query based on walking nodes. So you'd start at some node. This would be node 0. I guess manchecks was pointless, but you return a value out of X. In this case, presuming that node 0 has a field name, this would return that, and then you just execute as REST. Now you can wrap. I'm just using Faraday here, but you can wrap this stuff in helper code. So really, just be like, hey, execute the Cypher query and return. It would be very much like interacting with a sort of a relational database with just a different type of query language. There are other graph data stores too. Hypergraph is also a Java one, so you're not going to get away from that Java problem. And then there's FlockDB, which is a scalable graph data store. This is actually created by Twitter, and they use it internally. I think it runs on Scala, so I think it's also Java. FlockDB, you're almost, unless you are Twitter, there's a reason that most of you have probably never even heard of it. But I just throw it out there because it is possible to do sort of these distributed graphs, but it's so limited. I wouldn't take a serious look at it. I've looked at a lot of graph databases, and still nothing impresses me like Neo4j does. And the Cypher, to me, just sort of clinches the deal. And this is just sort of a list of different styles of databases and different things that you might want to write, might want to use for like FlockDB, social network. Other than that, I can't think of a purpose. I say MySQL and Postgres for a bank, although realistically I would probably use something like Couch for a bank, but I needed some sort of canonical example. Really, Postgres is sort of the go-to one. If you don't know these very well, then it's still a lot of the time what you're probably going to do. If you don't know anything, somebody asks this question, what do you do if you don't have any information about what the problem set's going to be? Then probably just Postgres, because it's still the one that has 40 years of experience behind it, and probably 50 years now. But at the end of the day, these all depend on your use cases, and the only way to know which one to use is to know them, unfortunately. I also have a list of a bunch of papers here that I think are really interesting. The CAP theorem paper is sort of the canonical NoSQL database understanding paper. Distributed data stores have their own sets of problems that are inherent. If you understand the CAP theorem, you'll understand why React is so genius, basically. Dynamo, which is what React's based on. Bigtable, which is HBase based on, MapReduce. This paper's not really even worth, I guess, reading, but just for historical value, it's there. And then there's other different types of data stores too. Peanuts is Yahoo's data store. Megastore, if you want to see sort of the future of where these databases are going, this is Google's newest data store internally. They're pushing this pretty hard, and we can talk about that if anybody's interested in discussing it. And yeah, that's pretty much it. So, all right, I lied. It was 30 minutes long. So, any questions?
I am kind of admittedly old school in my thought processes about databases. I have a hard time not shoehorning everything into a relational database. More often than not, though, I don't feel like I don't feel like I am shoehorning so much as just seeing relations where other people may choose not to. Like, see, you talked a little bit about having connections between hierarchies and document stores. This is one of the things to me that that always seems like a terrible smell in data modeling. Where you want to introduce relational data into a hierarchical structure. So, I mean, for my money, why wouldn't you just say use a relational data store that has the ability to store hierarchical data? Like we've been modeling data like that for God knows how long,
yeah,
and we've come up with some really efficient ways of doing it. Closure tree being one algorithm that that we've implemented on a recent project, or with Postgres support of HStore. When you have that mix of, and this is what we see most often, I think, that mix of relational needs and some subsets of hierarchical data, where that subset may in fact be a large portion of the system. Where do you draw the line? For me, I always tend to fall on the relational side.
Well, yeah, and I will say that when we were discussing which databases to put in the book and which not to, there was a lot of talk, and there was actually even some pressure to leave Postgres out. And it was actually the chapter that I had the hardest time writing, because people already know relational databases fairly well. There are some people that don't, and I didn't want to leave them behind, but I also didn't want to bore the pants off of people that it's like, all right, here's how you do a select statement, here's how there's a little bit of that in day one, but then it kind of ramps up pretty quickly to show all the really, like you said, there's a lot of really cool things that you can do with a relational database that people just don't know. And I think a lot of times people sort of have, at least my experience, have run across people that are saying, oh, well, I need to use Mongo because relational databases don't do X, Y, Z. And then when I tell them, it's like, well, they actually do. You can store an array in a relational database as a data type. You can, just like HStore, you can do that with arrays as well. You can store n-dimensional cubes, like the example I showed. So there's definitely a lot of power there. There's a lot of things you can do. Another one that I was amused by was somebody said, oh, I've got to use Mongo because I'm storing geographic data, and I need to be able to query nearest neighbor searches and things like that. I'm like, really? It's like, you've never heard of PostGIS? This project's like 10 years old. So part of it is, you're right, it's sort of an education thing. But, and the other thing is that SQL has been around for 40 years. think of any programming language that's been around and still currently widely used for 40 years. I mean, if that is the definition of success as far as I'm concerned. I mean, it's probably the most successful language out there. And it has remained relatively unchanged over that time, which is a testament to how great it is. That said, these NoSQL databases didn't arise up in a vacuum either. It's not like somebody just sat down and said, I hate Postgres, I want to write something entirely different out of left field. I mean, these came out of real world pains and real world problems. Like, for example, Dynamo. You reach an upper limit on what you can do with a relational database, and at a certain point, you stop using it as a relational database. Like you said, and I noticed you sort of started going down sort of the backtrack a little bit, said, I don't feel like I'm shoehorning, but you kind of are. Once you start sharding a relational database, you've sort of lost the power that makes it a relational database. You can't really join across shards, not in any sort of reasonable way.
Right, that's when you give up consistency.
Yes, right, exactly. And I guess I mentioned the CAP theorem a couple times, just sort of the conversational way of saying it is, CAP theorem is that you can have a system that's consistent, like internally consistent across the entire system. You can have something that's available, meaning that it will always serve response to all requests. And you can have a system that's partition tolerant, meaning that if a partition appears in the system, that it's tolerant of that, and the whole thing won't come crashing down. Which basically means it's distributed, because you have to be partition tolerant if it's a distributed system. The CAP theorem says you can only pick two of those. You can be, you can be consistent or you can be available, but you can't be both if you're a distributed system, effectively. And so, like you said, you lose consistency once you start sharding data, because the relational database wants to be available. You could easily go the other way and then make an argument. Make a rule and says, you know what, I just won't serve any requests if a partition occurs, in which case it will remain consistent. It just won't be available to requests, which is every bit as bad as just not being up at all. So back to that, that like React, for example, they wanted the flexibility of being able to choose which of those theorems, which of those things they wanted to give up at a certain point in time. So if you're doing like session management, you probably don't care so much about consistency as availability. I mean, if you happen to lose somebody's session ID and they have to log in again, so what? It's not the end of the world. It's much more important that it very quickly responds, because if somebody's sitting there waiting for your highly consistent data store to just return a user ID, they're just going to leave and go somewhere else. They're just going to be like Amazon.com, such a joke, and quit. On other standards, when you're making a payment, for example, consistency is paramount. You don't want to lose that information in the middle of a transaction, for example. Availability isn't quite as important. If people click a purchase button, you may as well make them wait for a few seconds, because they've already clicked the button, they've already bought it. You just want to make sure that what they get is the correct result. So that flexibility is exactly why these occur, and you can do those things with relational databases. But what you find is you start making sort of exceptions and edge cases and be like, all right, well, here's my transaction management portion of my system, and it's set up and deployed in its own way. And then here's my session management of my relational system, and it's set up and managed in some special way. So that's sort of my answer to that, is of course you can do all these relations. And in fact, you can probably do everything that you would ever need to do with any single one of these systems with enough code. But the question comes down to is how easy is it to do?
Sure.
And in some cases, it's not very.
Yeah, so I mean, the choice of graph database for a recent project, I think illustrates that point. The querying the sort of data where we needed to know how many steps removed someone was in a social graph. That could have been done in a relational database. In fact, using ClojureTree, you could get that data relatively easily. But given the sophisticated query language around it, and the fact that that's something that whole database is meant to do. The assumption is that we save a lot of code and effort by going down that route.
Yeah. And it really does. It very much comes down to effort. It's not that. And I think probably one of the best examples again is Twitter. They still use MySQL. They sharded the hell out of it to the point where it resembles the MySQL you're used to dealing with in almost no way.
Wow.
But it's still at its core MySQL database. And I mean, this is of course my understanding. I mean, they may have totally ditched it by now, but as of last I heard, it was still MySQL, and there are other companies that use relational database in that way. So, again, it's not so much that you can't do it; it's a should you do it. Unfortunately, the only way of knowing is just knowing them.
Yeah, and so I guess for me, the interesting point still remains, how do you begin to draw that line, right? Like even when you're familiar with them, and perhaps you even endeavor in some exercises that might be purely academic, just to get to know the platform. But at what point do you do you make the choice? I guess it's always going to be on a case by case basis, and sometimes it'll be things like hardware, like we're currently having issues finding stable third party Neo4j hosting. So this is an issue. So there's always going to be considerations like that. But specifically, the thing that we run into the most often here is like we've got some hierarchical data, we've got some relational data. I mean, are there any kind of good general rules for deciding which direction to go, or how do you go about resolving things like that, where you've got some data that really wants to be hierarchical, but you've got your typical system that has a lot of relational data. Like, how do you go about making decisions?
Yeah, no, that's actually a really good question. And I'll give an example of how I'm still learning about how these different systems can be used. When I gave the list up of different databases and the applications that they sort of excel in, I had originally put up there Postgres MySQL for banking application. And at the time when I wrote this, I actually believed that, because I was like, oh, you've got the whole ACID transaction thing. And then I spoke with somebody who actually wrote bank software in Couch, and they were explaining that actually that's not how bank software works at all anyway. They don't do the sort of the canonical transaction example. People have probably heard the argument for ACID transaction is, okay, you've got Alice and you've got Bob, and you debit Alice's account by $30 and you credit Bob's account by $30, and if a crash occurs in between, then the system would be in an inconsistent state, so that's why you need ACID transactions. But banks don't actually work that way at all anyway. What they really do, and as anybody who's gone through their bank statement knows, is it gets posted and then it's pending, because it just writes that transaction as a row in a table somewhere that then gets resolved in like 24 hours. I mean, that's not ACID in any conceivable way. That is eventually consistent. That is like the very definition of eventually consistent. And so the reason I would use something like Couch to that is because it is a very ridiculously stable system, down to the point it's called crash-only design, where you don't. It's written in Erlang, and so in Erlang, when it writes to table, it writes values out into the file, but the file can never be corrupted, because worst case, that write just wouldn't succeed. And so you don't gracefully shut down Couch instances, you just effectively just crash them. And you kill it, and so it just crashes it. But it doesn't matter, because either a write is finished or it's not finished. If the write is finished and it's usable, that was a successful write. If it wasn't, then it was an unsuccessful write. And you would be amazed at how much this simplifies your software setup, when you don't have to worry about something like Mongo. If Mongo crashes mid-write, you have to do a repair on it. And relational database, on the other hand, have all of this overarching framework in order to sort of deal with being able to handle these sort of crashes. So anyway, the point being with that is that I can sit and say, these would be my recommendations, but learning more, I might have a totally different set of recommendations in a month as I've learned more as well. It comes down to knowing the domain well and understanding the database as well. And unfortunately, there's not really a better way of going about that. There's some general cases that I would probably say. If you need to embed something, well, if you need to embed a database, there's a whole class of database that you can just remove from your problem scope. You can't possibly embed React. You can't embed Mongo. You can't. But what you can embed Couch. You can embed Neo4j. You can embed, maybe not Postgres, but like Berkeley DB or SQLite or something like that. So your options start getting whittled down, and so that's sort of how I make the decisions is as I figure out what are my requirements, and then start removing possibilities until I'm sort of left with a couple. And then at that point, it actually can just be a preference thing, and it's like I just like this one better. Sort of long drawn out answer to your question.
Yeah, I think it's hard to escape the Polyglot, database environment. That's basically what we're doing. We set the system of record to be one of them. But actually, I had a misconception of what the system of record was. Do you mind explaining when you do have to deal with a Polyglot database environment where you have, like, say, Postgres, and then you let Neo4j do the heavy lifting for the social aspect of the relationships within the nodes or the users or whatever, and then it's very easy for us to query the degrees of separation there. In our case, what I thought was the system of record was going to be everything. I could take everything from Postgres and recreate my graph database. That was my definition, rough as it may have been. That's what it is right now.
Yeah.
But what would you describe a system of record to be?
And for a system your size, I think that's probably, for your size, that's probably a fair definition. But I mean, really, I define it as based off of domains. So you just need to know, okay, so here's my user data. Here's my, access control data. They don't necessarily need to be the same database. You just need to know that this domain of data is the canonical one when you have polyglot systems. That's sort of the general definition. You just need to know who wins on a domain by domain basis if there's ever a conflict in the data where they're not necessarily in sync. Who comes out the victor? Is it the Postgres database or is it the Neo4j database? And it doesn't have to be universal across your entire data set. It just needs to be pretty much universal across domains, just so it doesn't get confusing. I mean, if you really wanted to be pedantic about it, you could even do a table by table basis or something like that. But domain tends to be a pretty good sort of measure. But again, if it's a small system, that's a fair definition. Because
earlier when we were talking, you mentioned the database that you left out. Would you mind telling everybody a little bit about that?
Sure. The fifth element. It was called OrientDB. OrientDB is pretty awesome actually, and it was actually originally going to be in the book, and we removed it in favor of Couch simply because we had just so many people asking. It's like, you cover Mongo, why don't you cover Couch? And it was a fair argument, and we ended up just including the book just so they can counterpoint against each other. Where even though there's both document data stores, one has clear advantages over another in certain problem scopes. But OrientDB is interesting. It's a class that I didn't put up there because it's sort of a hybrid. It's a hybrid database. Orient can act as a key value store. It can act as a relational. It can act as a graph data store. It can act as all these different sort of databases with the same set of data underlying. And that's what I find kind of fascinating about it. I'm not sure if we're going to evolve to that point where all these databases sort of become this hybrid model, but you do sort of see it now in some small forms, and I'll give a good example, is that Mongo and Couch started off as different as two document data stores could possibly be in the beginning, but over time they've been sort of going like this to each other. So Mongo originally didn't have MapReduce built in, and now they do because Couch had it, and people would be like, hey, why doesn't Couch have this? And then Couch, despite its ability to replicate, it didn't have any sort of service where you could easily manage those replicatable databases, and now there's Big Couch, and there's Couchbase is another one, and so it's sort of going into sort of the web scale Mongo territory, so they've sort of jumped up. And so they keep getting more features added to them. Redis, for example, key value store, but then people are like, oh, but how do I manage certain kinds of message patterns like blocking queues and pub/sub and things like that? And Redis added that kind of to it. So as these databases sort of get more and more and more aspects added to them, I think you're going to start seeing the lines between these sort of, right now they're still fairly clear, but the lines between these blurred, and you'll be like, what kind of database is this? Is this a key value store, or is this a document data store? Actually, React is sort of going that way too, because it used to be just a straight up key value store, but now you can do things like indexing. You can actually index data in React, which is very much not a key value store type of thing.
Odd.
Yeah, and you can do, and because it uses Lucene right now, so you can do sort of partial queries and things like that, and be like, give me all of the values where where the keys start with Joe and then asterisk, and then it'll return it. So they're very much kind of encroaching on each other, because there's so much money in big data. Look at Oracle. It's one of the biggest companies in the world for years, and all they do is database, really, and that's how important data is. And I think it's actually kind of amusing that it sort of took the industry years to realize, oh wow, there's actually a lot of money in being able to manage people's data. And so I think that's why you're starting to see a lot of these feature sets. Because if you look at all these databases, every single one has a company behind them. Except for the possibility of HBase. I'm actually not sure. I guess there's Cloud. They might be considered a company behind it, but I think they're more interested in the Hadoop part. And that's a kind of a good and bad thing. The good thing is the fact that when there is a big company behind these databases, they'll be around tomorrow, because there's a lot of money riding on them. The downside is there's a lot of money riding on them, so you're going to see weird things popping up, just like you did with Oracle, where in the 90s you'd be like, hey, here's our XML extension to Oracle, so that you can write XPath queries, and it will go into. It's like, why would anyone want this? And nobody, a few people, but not many people actually wanted it. But it became bigger and bigger and more bloated.
Apparently, you never wrote any Java server phases.
I did write Java server phases, so. But not against Oracle, no. Yeah, that's a good question.
So the OrientDB thing sounds really neat. Because it seems like most of the systems that we write, kind of converge on being some sort of hybrid anyways. We tend to hybridize in our application stack, so that we have access to these different data stores that we need in the manner that we want. But yeah, it'd be great if there was this homogenization layer where it dealt with storing all of the underlying data and then exposing these different methods of defining relations or
it would be amazing. The downside is you have to write Java code.
Oh yeah.
For a lot of it, yeah. Now that said, this is why I'm kind of excited about Cypher, because I'm hoping that Cypher becomes sort of like SQL did with relational databases. It sort of starts removing a little bit of that vendor lock with graph data stores, and then there's like HQL for Hypertable. I wish they wouldn't have named it that, because it's very much just that company. But I'd love to see more of these query languages for each of these databases. But it's still such a young thing. It's such a young industry. Again, these things came up from real specific use cases, And so most people who are interested in Couch right now don't care that they have to write JavaScript MapReducers. That will change as less and less. It stops being so much of a programmer-centric thing and starts being more of a data analyst-centric thing, which it will. I mean, it almost certainly will. So it's sort of a neat time to be in this space, which is funny because it's like I've been involved in databases since like the mid '90s, way before it like wasn't cool at all. People be like, "Why are you doing databases?" I'm doing networking, and all of my friends went to like security classes, and it's like I got another database class to go to, and now I'm laughing as they're. I was gonna say something snarky. Yeah, it's technology. You know what? In 5 years, like, you did databases? That's so lame. Everybody's just doing holographic images now.
It does kind of seem like a lot of these databases that are kind of springing up, they come from like niche market. You know, they have a niche need. There's a company that has a specific need that they're trying to, and then it does get diluted once it kind of gets out into the real world. And people say, well, you know, that's great that it does this, but it should be able to do this, this, and this. And it's like, well, as opposed to taking these and expanding them out, use them for what they are, and accept that that's what they are, that's all they're going to do, and it serves a particular niche, as opposed to, you know, it is kind of like the thing. In all honesty, yeah, for the most part, most companies can use a relational database and get away with it for the entire extent, you know, of their lifespan. But then you have companies that come up with, I think too often they try to jump on, oh, this is the latest and greatest thing, this is going to be awesome, and then they're like, oh wait, it doesn't do this, this, and this, and then like, well, here, let's tack this on, and then you do run into things like system of records and things like that. Well, where do we store? You know, what is the winner here? Is this, you know, is our Postgres database going to be in control of everything? Or are we going to distribute data out? You know, or we've got a Mongo database over here handling document storage. We've got our Postgres database, and now everything's distributed all over the place. And it's like, oh wait, if we would have just found one solution, you know, and it does end up being a hybrid solution. There's not,
rather than even just finding one solution, just accept the fact that your application may in fact be the hybrid layer rather than
So
yeah. But it's sort of like object oriented. You know, I know people that cannot think in any other way than object oriented, and then Node.js popped up, and they're like, "Oh, this is just crappy. It's terrible. You can't do true encapsulation." It's like, well, it's not what it's made for. You can't do true encapsulation, which is actually one of its strong points, because it's not a classical language. It's a prototypical language, and I mean, it definitely takes a little bit of a mental shift, and you know, it's sort of like, again, it's like, I know a lot of people that are still obsessed with Java, and they will not touch Ruby because the idea, and they'll cite things like, oh, but the fact that you can override classes like string is just the worst thing on earth. Like they viscerally just they can't articulate why, or they can't articulate why. Unfortunately, endlessly, 5 million reasons on why it's the worst thing. But it's really more of a visceral reaction than it is a realistic one. Because when you tell them, it's like, but we're doing it. You know, it's like when they say you can't do that, it's like, well, yeah, I can, because look, it's being done. I kind of have that same reaction about the idea that everything is relational, and that you can, of course, model everything relationally, optimally. Well, I mean, of course you can, but that doesn't mean that it's the best tool for the job in all cases. Like Redis, for example. I mean, you can. Here's okay. Rescue, in my opinion, is much better than delayed job. And it uses Redis under the covers, and I think that's actually the reason that it's a better product, is because of the different database that it uses. I mean, it's as simple as that. I mean, yes, again, it's one of the cases you can use a relational database, but nothing about this is relational. It's just holding values and then popping them off the queue. I mean, why do you need a relational database to do something like that? I mean, you can, but should you? So, and I think you can ask that about any domain, really, and say, okay, is this the right tool for this domain? A lot of times it's not a clear answer, because like delayed job, you can use what you're used to. Is it what you should? I don't know. It's up to your boss.
Actually, the idea of like the CouchDB with the transactionless processing, that's actually something that is really cool. It's something I've kind of looked into for a while because, and I come back and please don't everybody scowl at me from a SQL Server background. I've been in SQL Server for years, and of course everything is like wrapped up in these transactions, so that you can make sure that the data stays valid. You know, it's the data integrity, managing it. The idea is like, well, okay, if the system crashes, the system crashes. Now you've got all these transactions that have to be rolled back and reapplied. Just don't do it. You know, just stop and just don't do what you're doing. And you know, so the whole idea of the CouchDB, almost like just basically everything just crashes and it's done. And you just kind of.
And before crediting CouchDB too much with that, that's actually a product of Erlang, really, because React has that same crash-only design. That's definitely an Erlang thing. But they took advantage of that by the way that they implemented it. Now the downside, of course, is with Couch you're back to the days of compaction, because it just keeps writing revisions, like new versions. So when you make a change to an object in Mongo, it will alter it just like a relational database does. It'll be like, all right, here's your block on disk, and it'll just replace this value with another one. That's of course why it can get corrupted, because midway through that write, it could fail, just like a relational database. Whereas Couch, it just would be like, okay, well, here's my document. Now here's a new version. It just keeps appending on to the end of the file. Now, of course, it's going to explode on size, so you've got to occasionally compact it, in which case it'll just remove all the old revisions and then just leave you with the most recent ones. So there's of course some trade-offs with it.
Well, that comes in handy too. A lot of companies, especially with some of the restrictions now put on, you have the whole idea of auditing. Your audits are basically kind of created for you, it sounds like, with your...
Yes and no, until you run a compaction, in which
Right.
case you've lost your entire history.
Yeah.
You can just ask people, please don't run a transaction. Don't do anything. Don't do anything bad, and then please, if you do, don't run a transaction after or a compaction afterwards.
Looks like it might be a good time
Cool.
to wrap.
Yeah.
Thanks, Eric.
Oh, it's so nice and stale now.